Hello everybody, we continue our lectures. Today the first section is the number E. So here we define the special number, very important number in mathematics, and the definition is standard. I mean, it's quite usual, but the proof may be given in different ways, and I prefer a slightly different way, so it will be given in a different manner than in your lecture notes, but you can use any of the proofs as you want. So we consider the sequence an 1 plus 1 over n power n, and we want to use the Weierstrass monotone sequence convergence theorem, and so what we'll prove? Firstly, the first claim is that the sequence is increasing. In fact, strictly increasing, but so how to prove it? One way is just to consider the ratio between two terms, an and an plus 1. So let's write it. What is it? An plus 1 means we substitute instead of n plus 1, and an just as it is. Now, what is it? We'll use properties of powers, so 1 plus 1 over n plus 1 power 1 I'll consider in a different way, and everything else I'll put into one ratio. So we split the exponent n plus 1 into two parts, n and 1. 1 is here, n is over there. Then here we have 4 stars, so we may simplify it to make just a usual fraction. So the first term will be n plus 2 over n plus 1. Now this huge expression, so we have n plus 2, right? Then n plus 1 is in denominator, but also here in denominator we had n plus 1 over n, so n goes to numerator and n plus 1 to denominator. That is what we'll obtain. Then let me rewrite it as n plus 2 over n plus 1 times n squared plus 2n over n squared plus 2n plus 1. Then you see very similar expressions as numerator and denominator, so I'll add and subtract the same one. Nothing changes. And then this is n plus 2 over n plus 1 times, so we divide, that is 1 minus 1 over n squared plus 2n plus 1 power n. And then recall Bernoulli inequality. Bernoulli inequality, 1 plus alpha power n greater or equal 1 plus alpha n for alpha greater minus 1 and natural. We proved it some time ago. So, and I'll take this as alpha. Alpha is negative, minus 1 over n squared plus 2n plus 1, but it satisfies the restriction alpha greater minus 1. So, greater or equal, by Bernoulli inequality, n plus 2 over n plus 1 times 1 plus alpha, alpha is minus 1 over n squared plus 2n plus 1 times n. That is by Bernoulli inequality. Then, if we transform this expression, so common denominator is here, n squared plus 2n plus 1, and so I may write as one ratio now, n squared plus 2n plus 1, this one. And here what we have, n squared plus 2n plus 1 minus n. So n squared plus n plus 1 plus 2n plus 1 minus n. Then what is it? What is it? Let's open brackets. That is n cubed plus n squared plus n plus 2n squared plus 2n plus 2 over and in fact this is, look, what is n squared plus 2n plus 1? That was n plus 1 squared. So we multiplied n plus 1 squared times n plus 1, that is n plus 1 cubed. So I'll use the formula for the cube, and that is n cubed plus 3n squared plus 3n plus 1. So what is in numerator? N cubed plus 3n squared plus 3n plus 2 over n cubed plus 3n squared plus 3n plus 1. So both numerator and denominator are positive numbers and numerator is greater, hence that is greater than 1. And look at the beginning, an plus 1 over n greater than 1. So that is proved. An is increasing. Next claim which we have to prove is an is bounded above. Again, there are different ways to prove it, and I'll use similar considerations, but for another sequence. So let us consider another sequence. 1 plus 1 over n power n plus 1. So, obviously, an less than bn for all natural n, right? Hence, our claim that an is bounded above shall follow immediately if we'll prove another assertion, another claim, that bn is decreasing. And how we can prove it? Again, by similar assertion. But now we should divide, if we want to use again Bernoulli inequality, then I'll consider the ratio bn over bn plus 1, not bn plus 1 over bn. So, what is it? 1 plus 1 over n power n plus 1 over 1 plus 1 over n plus 1 power n plus 2. That is, again, 1 plus 1 over n, 1 plus 1 over n plus 1 power n plus 1 times 1 over 1 plus 1 over n plus 1. So we split n plus 2 into n plus 1 plus 1, n plus 1 plus 1. Then similar transformation to that one gives n plus 1 squared over n times n plus 2 power n plus 1 times n plus 1 over n plus 2. Then, that is n squared plus 2n plus 1 over n squared plus 2n power n plus 1 times n plus 1 over n plus 2. And again, let us use the Bernoulli inequality. Now alpha, here, okay, let me write once again, 1 plus 1 over n squared plus 2n times n plus 1 times n plus 1 over n plus 2. And that is greater or equal, so alpha now is, in Bernoulli inequality, is 1 over n squared plus 2n. And power is n plus 1. So we have 1 plus n plus 1 times 1 over n squared plus 2n times n plus 1 over n plus 2. And let us write again like that is n squared plus 2n plus n plus 1 over n squared plus 2n times n plus 1 over n plus 2. That is, okay, maybe I'll write the result. So n cubed, then we have 3n squared plus n squared plus 4n squared. Then how many n's? 3n plus n plus 4n plus 1. And what we have? in denominator, n cube plus 2n squared plus 2n squared plus 4n squared plus 4n. And that is again greater than 1. So the claim is proved. We have proved Bn is greater than Bn plus 1, so Bn is decreasing. And why it implies our second claim? Because look what happens now with our sequences. Let me write the chain of relations between An and Bn. So A1 less A2 less A3 and so on. And from the other side, okay, let me write like that. From the other side we have the chain of inequalities in another direction. Right? So you see, An is always less than Bn. Then An is automatically less than all members before. So, for example, An is smaller than B1. So we have for arbitrary n, An less than B1. And what is B1? This is 4, right? B1 equals to 4. So we have now both suppositions of theorem about monotone convergence, Weierstrass monotone convergence theorem for sequences, and it follows now An is increasing and bounded above, hence there is a limit of the sequence An. There is a limit of our sequence, and this is by definition is the number E. Okay, I don't remember all digits, of course. 2.718281828. I mean, nobody knows all digits. And after that, other digits, twice the year of the birth of Leon Tolstoy, famous Russian writer. Yes, automatically, of course, that is obviously, there is a question, obviously, that the limit of Bn equals to the limit of An. Why? Because Bn equals to An times 1 plus 1 over n, right? If so, we now have a limit An equals to E, so then the limit of Bn is also E as well, right? And by the way, now we have E somewhere between, right? And it means that we have nice bounds for the number E, right? So, for example, if we take A1, that is very rough bounds 2 and 4, and of course you can use every n as you want to obtain better bounds for the number E. The number E is not rational, it is irrational, also it is transcendental number, so it is not a number which is a root of an algebraic equation with rational coefficients. Okay, so now let me consider next example. Let me write it down. Okay. Yeah. Okay, example. Let Pn be an arbitrary sequence such that limit as n tends to infinity Pn equals to plus infinity, and Qn and from 1 to infinity is such that the limit of Qn is minus infinity. So show that the following limits take place: n tends to infinity, 1 plus 1 over Pn power Pn equals to the limit is n tends to infinity, 1 plus 1 over Qn power Qn equals to E. Yeah. So, solution. So we know that maybe I didn't mention before what it means, those limits. This is the first time when we meet. Okay. So what means infinitely large sequences, and what is, maybe let's firstly give the definitions. Yeah. So what means the limit of Pn equals to plus infinity? By definition, it means that for arbitrary epsilon greater than 0, there exists number n natural, such that for all n greater than n, Pn is greater than epsilon. So sometimes to emphasize that, you see, here epsilon is arbitrarily large, in fact. So when we consider the definition of usual limit, we suppose that epsilon is arbitrarily small. And here, in fact, epsilon is arbitrarily large, what's important. And to emphasize it, sometimes one can use 1 over epsilon instead of epsilon, just to emphasize this. Of course, both are correct. Without 1 just being greater than epsilon, it's equivalent, because if epsilon greater than 0, then 1 over epsilon is also greater than 0, and it is arbitrary as well. And for the limit equals to minus infinity, we have analogous thing. But now this is less than minus 1 over epsilon. Or if you want just minus epsilon, doesn't matter. And there is a difference between many textbooks in Russian and in English. And the difference is in this plus. So in Russian textbooks, you can find also such a definition. So Pn in modulus greater than 1 over epsilon. So it means that, for example, the sequence has a limit infinity without sign, but because plus minus signs, hence neither this or that inequality hold. But the last is true. And in your text lecture notes and in most of textbooks in English, infinity here is the same as plus infinity. So it means this is not considered at all. That is a little bit strange, but there is such a difference. So we'll not use, so it means for your lecture notes this is not true, because limit equals to infinity is the same as plus infinity. But in that example it is written plus infinity, and this is good. Okay. So go back to the solution. Look, we know that the limit as n goes to infinity, 1 plus 1 over n power n equals to e. What it means? It means that for arbitrary epsilon greater than 0, there exists capital N natural number such that for all n greater than this capital N, we have modulus 1 plus 1 over n power n minus e less than epsilon. Now, let me write down the definition of this equality, limit of Pn equal to plus infinity. Here, I should write again such a chain of quantifiers, but let me choose as epsilon greater than 0, very special. So I'll put here, right? Let's take 1 over capital N, this natural N. That is positive number. So by the definition of infinite limit, we have there exists, okay, let me use another letter, of course, now, right? Let's say N1 natural, such that for all n small greater than this N1, we have Pn greater than 1 over n. Oh, sorry, 1 over n, so that is n. And what it means? It means that, look, that for all n greater than n1, I can, look, so if Pn is greater than capital N, then it follows that integer part of Pn is greater or equal than n also, right? Okay, so, and hence integer part of Pn plus 1 is greater than n as well, right? So, yeah, it means I should take here n plus 1, sorry, n plus 1, and then here n plus 1, then it is strictly greater than n. Integer part is strictly greater than n. So, now, it means that both numbers, integer part of Pn and integer part of Pn plus 1, are natural numbers greater than capital N. So, it follows from those 3 lines that we have the following inequalities. 1 plus 1 over integer part of Pn power integer part of Pn minus e is less than epsilon, and also 1 plus 1 over integer part of Pn plus 1 power integer part of Pn plus 1 minus e is less than epsilon. So both are satisfied because those are natural numbers greater than capital N, and for them, so I'll use them instead of small n here. Okay, in fact, we know that the sequence 1 plus 1 over n power n is increasing, and it means that in fact we know more precisely that 1 plus 1 over integer part power integer part less than e plus epsilon and greater than e minus epsilon. So this number is smaller than e for sure, so I may forget about this. And analogously over there. Okay. Let me recall, both inequalities are valid when n is greater than capital N1. Then, look, I'll estimate 1 plus 1 over n, Pn, Pn power Pn. So, I'll use only numbers n sufficiently large, so n greater than capital N1, so Pn is positive for sure, right? Then we have such estimates. So I'll need, in fact, estimates to both sides, to the left and to the right. So above. To make an estimate above, I should take something smaller than this Pn. What is smaller? Integer part. Integer part, recall, integer part of Pn less or equal Pn less than integer part of Pn plus 1 by definition of the integer part. So, Pn is greater or equal than integer part of Pn. I will use this one. Then, by the properties of powers, of course, we didn't prove all of them for real numbers yet, but okay, let us use them nevertheless. So this is less than, you see that the base of our exponent is greater than 1, hence if we replace Pn by something greater, we have strictly less. 1 plus 1 Pn power Pn plus 1. Okay? Yeah, that is 1 plus 1 over integer part of Pn power integer part of Pn times 1 plus 1 over integer part of Pn. Okay, let's have a break. Okay, let's continue. And by the way, I observed misprint here. Please correct. Okay. Now, look. Here, I may continue the estimate by this one, 1 over integer part of Pn power Pn less than e times 1 plus 1 over integer part of Pn. Now, let's go to the left. Analogously, I'll replace, so I want to write an estimate below. It means I should estimate Pn above. Pn above is this one. So 1 plus 1 over integer part of Pn plus 1 power Pn. Then I should estimate Pn here below, that is integer part Pn. And similarly to the left hand side, that is 1 plus 1 integer part of Pn plus 1 integer part of Pn plus 1 times 1 plus 1, not times, divided by 1 plus 1 over integer part of Pn plus 1, and that is greater than E minus epsilon times 1 plus 1 over integer part of Pn plus 1. Okay. Now, minus 1, right? We divide by. Okay. Now, look, analogously to, so I used the definition of the limit of the sequence 1 plus 1 over n power n. Now let us use analogously the definition of another limit as n goes to infinity, 1 plus 1 over n equals to 1, as we know, right? So what it means that for arbitrary epsilon greater than 0, I can find capital N2 natural, such that for all n greater than this N2, we have modulo 1 plus 1 over n minus 1 is less than epsilon, or 1 plus 1 over n less than 1 plus epsilon greater than 1 minus epsilon. So now I'll add one more thing, namely I'll choose I'll choose the definition that Pn goes to infinity now in a different way, namely here I'll choose, instead of epsilon, this this n2, right? So now I'll put here epsilon equals to n2. Again, 1 over n2 minus 1, n2 minus 1. Then we have there exists n3 natural such that for all n greater than n3 we have Pn greater n2. And if Pn greater than n2, then we have 1 plus, okay, I may write just 1 over Pn less than epsilon greater than minus epsilon. In fact, of course, here I may use just 0, because we know it's positive, right? So, then let me write once again what we have altogether. We obtain the following inequalities: 1 plus 1 over Pn power Pn less than, from one side, e times 1 plus 1 over integer part of Pn and greater than e minus epsilon over 1 plus 1 over integer part of Pn plus 1. Now, what we can deduce from this inequality? 1 over Pn less than epsilon. Then also okay, I may put here n2 plus 1 to have for sure that integer part is greater than, so it follows that integer part of Pn is greater than n2 plus 1. And yeah, I cannot deduce this one, sorry. Yeah, we have this one, integer part of Pn greater than n2 plus 1, and then 1 over integer part of Pn is less than epsilon. Because Pn is not natural, so we cannot substitute it here. But integer part we can. And analogously, 1 over integer part of Pn plus 1 is also less than epsilon. Both follows from the inequality Pn greater than capital N2 plus 1. So, then I can continue our estimates. Here, look, 1 over integer part of Pn is less than epsilon, so we have e times 1 plus epsilon. And from the left hand side, I can write greater than, so let me write it here, greater than e minus epsilon over 1 plus, so to make an estimate below I should estimate above that one, and that's again plus epsilon. So let me write down what we obtain. So for arbitrary epsilon greater than 0, we have found a number, namely which number? Maximum of n1 and n3 such that for all n greater than this maximum, all inequalities are valid for P with index n, and in particular E minus epsilon over 1 plus epsilon less than 1 plus 1 over Pn less than E times 1 plus epsilon. And look, what is it? E minus epsilon over 1 plus epsilon. I claim that E minus epsilon over 1 plus epsilon is greater than 1 minus epsilon 1. So for arbitrary epsilon, greater E minus epsilon 1. So for arbitrary epsilon 1 greater than 0, there is epsilon greater than 0 such that this is great, right? Why? Because why this is the case? Just multiply E minus epsilon 1 times 1 plus epsilon. And so what is it? E minus epsilon greater than E minus epsilon 1 times 1 plus epsilon minus E epsilon. So cancel this one, and we have epsilon times E minus 1 is greater than minus epsilon 1 times 1 plus epsilon. So that is very good. E minus epsilon greater E minus epsilon 1. E minus E epsilon. Yeah, that is for sure true for arbitrary. In fact, for arbitrary. It's too much. Greater than E minus epsilon 1. Yeah, it's true. It's true. So it's okay, right? And also this is less than E plus epsilon 1. Again, for arbitrary epsilon 1, there is such an epsilon, right? So it means finally we have the inequality which should be satisfied for the definition E minus epsilon 1 for arbitrary epsilon 1. There is such number, there is such that for all we have this inequality. And that is done. So yeah. It means we have proved the first part. Now for the second. Now for the second. With Qn. With Qn, we proceed as follows. So put alpha n equals to minus Qn. Then limit of alpha n equals to plus infinity. And now 1 plus 1 over Qn, power Qn, we can write as 1 minus 1 over alpha n power minus alpha n. That is alpha n minus 1 over alpha n power minus alpha n, or 1 over this, so alpha n over alpha n minus 1 power alpha n, and that is one plus 1 over alpha n minus 1 power alpha n, and let me rewrite it as 1 plus 1 over alpha n minus 1 power alpha n minus 1 times 1 plus 1 over alpha n minus 1. So if alpha n goes to infinity, then alpha n plus alpha n minus 1 goes to plus infinity as well. So by the proven part, the first term tends to e as n tends to infinity. The second term tends to 1 as n to infinity. So then the product tends to e, and that is done. Okay, that is about the number e. Now, next section, section 9.2. Bolzano-Weierstrass theorem. Definition. If nk is strictly increasing sequence of natural numbers, then such sequence x with indices nk is called a subsequence of the sequence xn. And let me solve an example. Are the following set subsequences of the sequence xn equals to n. So first 1, 3, so on to n minus 1, so on. Second 1, 2, 1, 2, so on. Third 1, 3, 2, 5, 4, so on. Fourth 1, 2, 3, 4, so on. Fifth 1, 0.5, 2, 3, so on. 1, 2, 3, 4. So answers yes, because here we have increasing sequence of natural numbers. Here the answer is no, because we have not monotonic sequence even. 1, 2, 1, 2, and so on. Here also no, because of that, not increasing. Here the answer is yes, so the sequence itself we have, so the sequence itself is a subsequence as well. Here the answer is no, since 0.5 doesn't belong to our sequence. And here the answer is no, since that is finite sequence. So, okay, now we can, theorem, Bolzano-Weierstrass theorem. That is just the Bolzano-Weierstrass theorem. Every bounded sequence has a convergent subsequence. Proof. So consider our sequence xn. So here is our sequence. We have infinitely many members. Some of them may be equal, maybe even all of them are equal, doesn't matter. But what we know, it is bounded. Hence, there are lower and upper bounds. So there is an interval AB such that all members of our sequence are inside AB. Okay, let me denote A1B1 to be just our interval AB. Let me draw a picture, right? So here is our first interval A1B1. We divide it by two parts, equal parts. So A1 plus B1 over 2, right? We have now two intervals, A1 plus B1 over 2 and A1 plus B1 over 2, B1. Altogether, they form our interval A1, B1 altogether. And now, what we know about our sequence? Our sequence has infinitely many terms. And we have two parts of the interval. The whole interval contains infinitely many terms. Hence, at least one of those two parts contains infinitely many terms. Because if both contain finitely many, then the whole interval also contains finitely many terms. So at least one of them contains infinitely many. Doesn't matter which of them, let it be that one contains infinitely many terms of xn. Let it be A2, B2. So we denote by A2, B2 such half of the interval which contains infinitely many terms. Okay, so that is A2, B2. Then again we divide by two parts and continue. So what means continue? We have the sequence of embedded, of nested intervals, right? The length bn minus an is equal to b1 minus a1 over 2 power n minus 1 every time we divide by 2. And each interval an, bn contains infinitely many terms of xn. Okay, then by counter nested interval principle, nested intervals principle implies there exists a point C which belongs to the intersection of all intervals an, bn. Okay, let us choose, let it be n1 equals to 1, right? So x and 1 is just x1, doesn't matter. It belongs to a1, b1. Then a2, b2 contains infinitely many terms of xn. a2, b2 contains infinitely many terms. Hence, there is an index n2 greater than n1 such that xn2 belongs to a2, b2. And we may continue. So next, a3, b3 contains infinitely many, hence there exists number n3 greater than n2, and so on. So then we can construct, for arbitrary k, there exists nk greater than nk minus 1, such that x and k belongs to ak, bk. So we have constructed a subsequence of our sequence xn. X and k is a subsequence of xn. And what we know, we know that x and k belongs to ak, bk, and also our point C belongs to the same interval. Hence, the difference between those two is less or equal to bk minus ak, what is b1 minus a1 over 2 power k minus 1. Of course, this is greater or equal than 0. As k goes to infinity, the right hand side goes to 0 and the left hand side as a constant sequence also goes to 0 as well. So 2 policemen guarantees that x and k tends to C. And that is done. So we have constructed a subsequence which has the limit C, so it is a convergent subsequence. The proof is completed. Okay. Now, definition. C is a partial limit of xn if there exists a subsequence of xn with the limit C, the limit C. Okay, in fact, maybe now cap several examples. So, example or maybe I'll change a little bit, example 2 for that section. So if xn is a convergent sequence. Then arbitrary then all partial limits coincide with C, with the limit of xn. So it doesn't matter which subsequence you choose. That is quite obvious. Okay, next example. Example 3. xn minus 1 power n. Here we have, it has two partial limits. Minus 1 and 1, because if we take all odd indices n, then we have 1, so we have constant sequence, it has a limit, the limit 1, and if we take n even, then if all are odd, then we have minus 1, and if n are even, then we have the limit 1. And last example, example 4, maybe not the last, I'll give one more, that if we take such a sequence, look, 1, 1, 2, 1, 2, 3, 1, 2, 3, 4, and so on. So every time we repeat more and more first members of the natural. Then every has partial limits n natural. So all natural numbers can be partial limits of a sequence. But one more example, example 5. As we know, the set of rational numbers Q is countable. Hence, Q can be written as a sequence. So we have such a huge sequence, and what are partial limits? Partial limits of that sequence are all real numbers. Why? Because you see that we have, according to the completeness axiom, we have in arbitrary small interval a rational number. So once we have a smaller interval, we have one more rational number, and so on, right? So it means we can find a subsequence of rational numbers which has as a limit an arbitrary given real number. So the set of partial numbers may be extremely huge. Okay, that's all for today. Thanks for your